Welcome to the third of our videos about the engineering properties of geometric shapes. In the first video, we looked at how do we find the centroid of a shape, whether that's a simple shape like this rectangle, a more complicated but still symmetric shape like this I-beam, or when we get into even more complicated, a shape that is not symmetric about top and bottom, but we still need to find I. Or we actually got into one really crazy, right, for about I and centroids, where we're looking at a composite shape made up of all different kinds of shapes: circles, rectangles, triangles, trapezoids, etc. So if you don't remember how to find the centroid of an area, go back and look at that first video. And then once we had finished talking about centroids, we looked at the moment of inertia. So centroid is a balance point, right? If I was looking at this I-beam and had cut out, or I'm sorry, this T-shape, and cut out the T-shape, if I put a balance point right under the neutral axis right here, the shape would balance about it. I still have some of the shapes we did. So for example, for this rectangle where we cut out an area of the top, that shifted our centroid from the original centroid of the rectangle right in the middle. It shifted it down a little. And so just the centroid, we always can remember, is easy to kind of imagine what it is. It's the point about which the area or the mass, whatever quantity it is you're evaluating, where they're all balanced about that point. But then we looked at I, the moment of inertia, which is not really a physical property that's easy to visualize. It is the bending stiffness or resistance to bending of a particular geometric shape. And the key idea when we're looking at I of composite shapes is we're always looking to find the total I about the neutral axis for the shape. So for a rectangle like this, it's really easy because the neutral axis of the shape is right in the middle, and so we're going to be able to find I in just one step. Looking at our equations for I, remember those are in our book. You can find equations for I off here to the side. So for rectangle, we're 1/12 BH cubed. So really easy here where everything is symmetric about the neutral axis. Again, reviewing when we get a little more complicated, here we can build a composite I from the individual shapes. But now, if we use the equation I equals base times height cubed divided by 12 for this top part, that would give us I about the centroidal axis of that shape we're looking at. So in that case, we have to use the parallel axis theorem to figure out how much is the I about this axis instead of the centroidal axis of the composite piece of the shape. And just same thing as we look at different shapes. Again, it just gets a little bit more complicated depending on what type of shape. Once we lose symmetry top to bottom, then we have to add the step of finding the neutral axis of the composite shape. Whereas if we look back at an I-beam, we cut these pieces out, but that didn't shift the neutral axis if we're bending about Y, right? Because it's still, we cut out pieces that their centroid lie on the neutral axis. That's not the case when we go to a T-shape. Again, if you think about the centroid of the big rectangle that could include this T, it would have been down here right in the middle. But when we cut out these two pieces along the edge, their centroid was lower down than the centroid of the parent piece, so that meant when we took those off, the neutral axis shifted up to maintain balance about that. And then lastly, we did that again for a kind of really complicated shape. We can find I for that as well. So again, if that's not ringing a bell how we did that to find either centroids or I, go back and watch the first two videos again. But in this video now, we're going to talk about Q. And we use Q as a term in the Shear equation. So if you remember from either the other videos, your text, or starting to solve problems, if we're looking to find the shear in a beam, if we think again, right, when we bend something, when we put a load that creates shear on a device or on an object, it is inducing shear along all the planes that make up the longitudinal axis of it. And there's also shear on the section that we're cutting. So the shear equation, if we're trying to find those shear stresses, you remember is tau is equal to the shear at that location, the total shear force, times Q, this geometric property that we're going to be focusing on today, divided by I, which we focused quite a bit on in the previous video. That's basically the stiffness of the shape relative to bending about the neutral axis. And again, remember that I that we find always has to be about the neutral axis. And then times T, which is the thickness of the section where we're evaluating for shear. So in this series, or in this video that we're doing right now, we're going to be looking at what Q and T are for different shapes. And so I said previously, and just in the intro to this video, centroid is pretty easy to visualize. It's a point about which the shape is balanced. I becomes a little harder, but it's easy to think about as the resistance of a particular shape to bending about its neutral axis. Q becomes even a little harder than I for students to visualize. What is Q representing? So I'm going to write out how I think of Q, and hopefully that will help. Just another way to say it, it's kind of a paraphrase of how Hibbler describes it in the strengths textbook as well. So Q is the moment, and it's the moment about the neutral axis of the cross-sectional area that is above or below, and that's important to note. You can find Q either by looking above or below a point where you are finding shear stress. Okay, so let's read through that. Q is the moment about the neutral axis of the cross-sectional area. Okay, so it's the moment about this neutral axis of the cross-sectional area that is above or below a point where you are finding shear stress. Another way that we say that as far as an equation is that Q is equal to y bar prime times area prime. So y bar prime is the distance from the centroid of the area above or below the point we're looking at, and then a prime is that area above it. So let's start with real simple shape, this rectangle, and start finding Q for different points in the beam. Hopefully you're comfortable with the idea that this is all about shear stress, right? And shear stress varies along as you move along this cross section. Typically a maximum here in the middle at the neutral axis, and then varying as you move closer or further away from the neutral axis. A couple caveats to remember about the shear equation. Again, this is not valid in areas, there's a couple different areas where it's not valid. One of which is when you're looking at a wide and shallow shape. So for example, it's not good practice to use this shear equation to find the shear in a section like this top flange of this I shape, because it's much wider than it is tall. So this equation doesn't actually represent shear very accurately there. So we don't use that there. Another caveat where we don't use it is where the section that we're looking at is not perpendicular to the outer edge. So if you had like either a curved outer edge or a tapered outer edge, anywhere that the cross section is not perpendicular, or I'm sorry, the plane through the point that you're interested in is not perpendicular to the outer edge, that's also a place where this shear equation is not valid to use. Okay, so that being said, let's work on, say we wanted to find the shear stress at point A. So we're not actually going to, I'm not giving you a V here, so we can't actually find shear stress, but we can solve for Q and talk about what T is. We already found I for this rectangular shape in our previous video. So I was 666.66 repeating centimeters to the fourth. So let's look at what is Q and T. So we'll start by looking at the area represented by the area Q, or how we find Q if we want to find shear at A. So let's say for finding shear stress at A, solve for Q and T. So T is the easiest one. T is the width of the cross section at the point you're curious about. So I'm going to draw in here a plane that runs through A, parallel to our neutral axis. So T is just the thickness of that cross section. So in this case, T is really easy. T is equal to 8 centimeters. Okay, now let's look at Q. A little more complicated. Q is equal to, we said it's y bar prime times area prime. Okay, let's talk about what the area prime is. So it says Q is the moment about the neutral axis of the cross-sectional area that is above or below a point. So here's the point. So we can solve for Q using either this area above A, so I could do it using this purple area. So let's do it that way first. We do know that we're going to need to know the distance. This y bar prime is the distance from the centroid of the area that we're looking at. So this is 2 centimeters, so the centroid of it is going to be 1 centimeter above that. So this distance right here from the centroid of the area that we're looking at, A prime, to the neutral axis. So this is y bar prime when we're looking at A. Okay, so let's plug in numbers for that. In this case, Q is equal to y bar prime. So from the neutral axis to the centroid of the area we care about, so it would be 5 centimeters to get all the way to the top. And this is 2 centimeters, so we come back 1 centimeter. So in this case, y bar prime, when we're considering the area of A, would be equal to 4 centimeters. And then the area of A prime, that's the area above the point that we're looking at. So that's 8 times 2, so that's 16 centimeters squared. So in this case, Q is going to be equal to 64 centimeters to the third. Okay, that's Q for when we're finding shear at A. So we would now have, we've already got I from our previous video. We now have Q and T. So if we knew what the shear force was applied across this cross section, we could plug that in and find the shear stress at A. So that was one way to find Q for the point A. That was using the cross-sectional area above the point we were looking at. But it says we can say or below. So let's solve it again using the area below. So in this case, that would be that big green area. So this big green area is 8 centimeters tall. So the centroidal axis of it is going to be 4 centimeters from the bottom here. So this distance right here to here would be 4 centimeters. So let's plug in and find Q using the area below. And it should come out to the exact same value, or else we've done something wrong. So Q for here is going to be equal to y bar prime. That's the distance from the centroid of the area I'm looking at. So that's the big green area. So that's right here, this centroid, to the neutral axis. So this is 4 centimeters. This is 5. So my y bar prime here is 1 centimeter. And the area, A prime, for this green area, it's 8 wide by 10 minus 2. So it's 8 high. So it's 8 times 8, so that's going to again be 1 times 8 times 8 is 64 centimeters cubed. So you can see it doesn't matter whether I use the area above the section or below the section. I should come up with the same value for Q. And that makes sense, right? What we're trying to find out here is what is just shear stress on this plane at A. And we know that it has to be balanced whether I'm looking at the piece of the shape that's below that plane or the piece that's above it. The shear stress on that plane should be equal, right? It's not like all of a sudden the shear stress jumps and changes from one side of an infinitesimally thin plane to the other. So it shouldn't matter whether you do top or bottom, so always just pick the one that's simpler. In this case, there isn't a simpler one, right? They're both just rectangles, easy to do. When we get on to more complicated shapes, it may be simpler. So, okay, that was finding Q at point A. Let's do it again now for Q at point B. So I should have said this is Q for A, for A. Now let's look at Q for B. So I'll do it in a different color here. So Q at B. Now here, so let me shade an area. So the area, if I'm looking at shear at B, then I can use the area either above or below. And you'll notice that B, I chose to put right on the neutral axis. So in this case, I can do above or below, like I said before, but in this case, the equation will be identical whether it's above or below, right? Because the shape above the neutral axis is identical to the shape below it for this particular shape. So it doesn't matter which I do. So I'm going to use the area below just since there's less things I'm coloring over there. So now this is the area I'm looking at is this kind of cyan colored area. Okay, so the centroid of this area that is 5 centimeters tall by 8 wide, so its centroid would be at 2.5 centimeters. So that's somewhere maybe there. Okay, so for Q, finding Q for B, y bar prime at B times A prime for B is equal to y bar prime is the distance from the centroid of the area I'm looking at, the cyan area below B, to the centroid of the whole shape. So we're at 2.5 and this is at 5, so it's going to be 2.5 centimeters is y bar prime. Area prime is 5 times 8, so it's 5 centimeters times 8 centimeters. So all that. .5 times 5 times 8. So it is 100 centimeters cubed. Okay, so you can see that at B, Q is significantly higher than it was at A, right? And that makes sense. There's a larger area that's being held onto the beam at B versus at A. So, yeah, and we've said that the maximum shear stress in a rectangular cross-section like this will be at the neutral axis. So we're going to find another one here. Let's look at C, and it should be less again than the 100 here. So now we're looking at C. Drawing's getting a little crowded, but so we're going to look at a plane cutting through C. So now the shaded area, I'll do vertical shading. So we're looking at C. So Q at C is going to be equal to y bar prime of C times the area prime of C. And it's important to always keep in mind that the y bar when we're looking at Q is different than y bar to the neutral axis. Y bar to the neutral axis is fixed for this shape, right? It never changes once we know the final composite shape. Like same thing for all these other shapes. Once we find the composite neutral axis of the shape, that is what it is. It's 5 centimeters, 5 centimeters. On this next one that we did, it's 6.5 centimeters. That neutral axis doesn't move depending on where we're looking at shear. So y bar prime and y bar will only be equal if we happen to be looking for the shear stress on the neutral axis. So that's a common confusion for students is they'll accidentally plug in y bar, the distance to the neutral axis, instead of y bar prime, which is the distance from the area we're looking at, the centroid of the area we're looking at, to the neutral axis. So yeah, I think that makes sense what I'm saying now. Okay, so in this case, the centroid of C, let's see, I know that C is located 3 centimeters away from the neutral axis. Okay, so C is actually a mirror of where A was up above. So it may not be intuitive yet, but just thinking about it, I'm thinking that our value for Q at C should be equal to the value that we found for Q at A, because it's mirrored about the neutral axis on a symmetric shape. But let's see if that turns out to be true. So the centroid of the area above or below C, so we're going to use the area below C, so that would be right here. So distance from its centroid is going to be 4 centimeters, 3 to get to the edge of it, and then 1 more to get down into the middle, so 4 centimeters, times the area held on here is 8 by 2, so that's 16, 8 centimeters times 2 centimeters. Multiply that, 16 times 4, we get 64 centimeters cubed again, which you can see that's the same thing for there. Okay, that is how we find Q for a really simple shape. And I guess I didn't talk about T again after that first one, and that's because T doesn't change anywhere along this shape, right? The thickness of the section that or the width, however you want to say it, of the section that's cutting through at A or B or C is all the same. T would be equal to 8 for all of those cases. Okay, let's go on and look at a more complicated shape. So for the next shape, let's look at the I section that we've previously found the moment of inertia for. So we got our moment of inertia is about the neutral axis. So again, we're now focusing on what if I'm asked to find shear at a couple different locations here. Again, the shear equation, remember, is going to be tau is equal to V, the shear across the whole section, times Q, the geometric property that we're trying to find, over I, what we found, the resistance to bending of this shape about its neutral axis, times T, the thickness of the cross section where we're evaluating for shear. So again, before we start plugging numbers in, let's think about what Q means as far as the scale. The larger the Q value is, the higher the stress is. And a way to think of that is another way to think about that is we're said Q is the moment of the area held on by a plane cut through the cross section at the point we're looking at. So the more of this shape that is held on by the cut that we're cutting through this beam, the higher the Q will be, and that means the higher the shear. And that makes sense. If we were cutting through down here, there's less material, less cross-section that is being held on by a plane cut through there than there is a plane cut through here or up at the neutral axis where it's balanced about that, right? So we talked about this before, that shear stresses will be highest right there at the neutral axis, and that means Q should be highest there too. Although we'll see, depends on how the thickness is, what's going on with that as well. Okay, so let's look at the equation for Q again. Remember that Q is equal to y bar prime times area prime, where area prime is the area either above or below the point that we're investigating for shear, and y bar prime is the distance from the neutral axis to the centroid of area prime. Okay, let's talk about the first point I have here, asking about shear, is at point A. And I picked point A to point out that if you're asked to find shear in a thin flange, like an I section here, you should not, that's not an appropriate use of the shear equation. Go back and look in your text. There's a whole section about limitations on using the shear equation, and one of them is you don't use it in sections where the width greatly exceeds the height because it doesn't accurately represent what the shear is. It would underrepresent the value of shear there. So at A, we're not even going to calculate it because you shouldn't be using the shear equation when you're in a wide, thin member. So the first one we're going to look at is B. So I'll use red since I've drawn it in red there. So Q, when we're evaluating shear at B, is going to be equal to the area prime held on by B times y bar prime for B, which y bar prime is the distance from the centroid of the area held on by B to the neutral axis. So let's draw that on here. Okay, so this is going to be a composite because there's two different shapes that are contributing to the area held on by B. So we can see there's a first area, this rectangle that's the top flange, and then there's another area right there, and I need to separate those because they're a composite shape, right? I have to know the centroid distance, and it's not intuitive where the centroid of that composite shape would be. It's obviously going to be slightly below that upper one, but we don't know exactly where, or I mean it's going to be somewhere right near that junction there. So we will work it in parts. So QB is going to be equal to, let's call this area prime B1 times y bar prime B1 plus area prime B2 times y bar prime B2. And we'll call this up here is B1 and this down here is B2. Okay, so centroid of area B1 is going to be right there. Centroid of B2 right there. So let's start adding values into our equation. Q at B, area B1 is 8 times 1, so 8 centimeters times 1 centimeter. That gets me the area of B1. And now I need to know the y bar B1. So that's the distance from the centroid of B1 to the neutral axis. So in this case, that's going to be distance from neutral axis to the top is 5, and then the centroid is, since the height of it's 1, is going to be half down, so that's going to be 4.5 centimeters. Okay, so that'll give me the component of Q from the top piece, and now we're going to add to that the area of the little piece here, which if this is 3 centimeters, and the total from here to there is 4, so area is, this here is 1 centimeter then. So 1 times the width there is 2, so 1 centimeter times 2 centimeters, that's the area of B2, and then times the distance from the centroid of B2 to the neutral axis. So that's going to be 3 centimeters plus a half a centimeter, so 3.5 centimeters. So let's plug all that in there. 8 times 1 times 4.5 plus 1 times 2 times 3.5, and that comes out to 43 centimeters cubed. Okay, just to point out that we can, let's do it again looking at the area below B, and we should find that Q is identical. This is something that, again, students often struggle with when they're first thinking about Q, because we're thinking it is an area, and so this is a much bigger area, right? So it doesn't seem like it could come out to the same, but the key difference is it's an area times the centroidal distance, right? So this big area here, for example, that we're going to use right now, its centroid is actually really close to C, right? Because if we look at it, the centroid of, well, let's go ahead and color these areas in. So let's do, so that's one area, a rectangle down to here, and then we'll do this as a second area. And to keep things clear, we'll call this area the green area, we'll say that's B3, and this area down here will be B4, because we're still finding Q for the point B. So QB is equal to area prime B3 times y bar prime B3 plus area prime B4 times y bar prime B4. Okay, let's start with B3, this rectangle here. It is a height of 7 centimeters. We can see from here to here would be 7 centimeters. So its area is going to be 7 times the width of 2. So QB is equal to 7 centimeters times 2 centimeters. That gets me 14 centimeters squared area. Its centroid would be located half of its height, so that's 3.5 centimeters from here, which that's going to be then, this from here to here is 4 centimeters, so centroid is just half a centimeter down from the neutral axis. So the distance y bar prime B3 is going to be equal to 0.5 centimeters. That's this distance right here. Okay, so that gives us the contribution to Q from this piece. Now let's look at B4. So plus the area B4, and that's 1 times 8, so 1 centimeter times 8 centimeters, and now times its centroidal distance. Centroid's right there. So from the neutral axis, we come down 4 to get to here, and then another half to get to the centroid, so times 4.5 centimeters. Let's plug all that in, and we should come up with 43 centimeters cubed again. 7 times 2 times 0.5 plus 1 times 8 times 4.5. Yeah, and the value again is 43 centimeters cubed. So the key idea there is how does this much larger area come to the same value of Q as the small area? And it comes down to the distance, that y bar prime, the distance from the centroid of each component to the neutral axis. If we look at these two equations here, for the top flange and bottom flange, for basically B1 and B4, it's identical, right? If you look at this term right here and compare it to this term right here, for Q, they're equal, right? 8 times 1, that's the area of the flange, times the distance to the neutral axis, that's the same. So the part that's different between the two ways, whether we look above or below, is the term that we called B2. Let's look at this one here. It's a pretty small area, right? It's just a 1 by 2 centimeter area, so 2 centimeters squared, but it has a distance from its centroid to the neutral axis of 3.5. Whereas if we look down here, it's a much bigger area, right? 7 times 2, so that's 14 centimeters squared versus 2. So that's a factor of 7 times bigger area. But look at the centroidal distance, 3.5 by 0.5. And again, that's a factor of 7, right? 3.5 is 7 times as big as a half centimeter. It's just swapped. So we got 7 times bigger area if we look at this bottom section, but we've got 1/7 distance of the centroid of the composite piece to the neutral axis as we do if we look at this little piece up here. So that's kind of thinking through why we can end up with the same Q when we look at very different areas, because we're weighting them by the distance from their centroid to the neutral axis. Okay, let's do Q once more for this shape and finding it at the neutral axis, where again we've said we would expect shear stress to be highest, so we would expect Q to be highest as well. So now we're looking at cutting along C here. So I'm going to shade it, the area we're looking at. We'll use the area below just to try to keep it from getting too crowded in here. That purple's not really standing out. What color could I use? Let's see if this shows up any better. So there's one piece, and then There's another piece. So let's write out Q at C. So we'll call this area C1 and this area C2. So it's going to, again, be area prime C1 times y bar prime for C1 plus area prime C2 times y bar prime C2. Okay, so Q looking at C, and we're symmetric about the neutral axis, right? C lies on the neutral axis. So not only would it be the same if I did Q above or below, but actually the equations will literally write out the same as well because everything's symmetric. So I'm not going to do both. I'll just do the bottom version. So area C1, that's the area of this rectangle right here. So that's 4 centimeters high by 2 centimeters wide. Okay, and then times the centroid distance from centroid of C1 to the neutral axis. So if this distance is 4, we know that the centroid would be at 2, so times 2 centimeters. That's y bar prime C1. Okay, now let's look at the second term for this bottom flange. So area of C2 is 1 centimeter times 8 centimeters. That's the area of this part. And now we need to do y bar prime C2. So that's the distance from the centroid of this bottom flange to the neutral axis. So that would be 5 minus 1/2. So times 4.5 centimeters. So let's plug everything in. 4 times 2 times 2 plus 1 times 8 times 4.5. 4 times 2 times 2 plus 1 times 8 times 4.5. So we get 52 centimeters cubed. That's the value for Q at C. And I guess we didn't talk about T here. T at C, that's equal to the width of the section at C, so that's 2 centimeters in this case. And at B, T at B is also 2 centimeters, right? They're both cutting through the web, so T at B is also 2 centimeters. Most people don't get confused about T. Okay, that is how we would find Q for different points within an I section. And again, remember, you shouldn't be using this equation if you're looking at a wide, shallow member. So don't use it. If you catch yourself trying to find Q up in this top flange, stop what you're doing and rethink. And for our next shape now, let's look at the T section that we previously found the moment of inertia about. So I have three different points here that we're going to look at Q. Again, remember, all of these that we're looking at is for the purpose, if we're finding Q, it's because we want to know something about shear. So we're looking to complete the equation. Tau is equal to V times Q over I times T. And we already found I. V is a property of the load that's applied to the cross section. So we're looking for the geometric properties Q and T. Okay, so this T section, we found a neutral axis, a composite neutral axis. It shifted up from the original neutral axis if we looked at a large rectangle. Again, if you don't remember how to do that, go back and look at the first video about centroids and then the second video about finding the moment of inertia about that centroid, because the centroid represents the neutral axis. In our moment of inertia, we always find about the neutral axis of the composite shape. So once we've done all that, we're ready. We've got I. We would be given or find V at the point that we're interested in. And now we need to find Q, which represents the moment of the area above or below the point where we're trying to find shear. So the first point I've asked us to find shear is about the neutral axis itself. So let's break this into pieces. Again, as always, we can do it either above or below, and we'll do it again both above and below for A here to just show that it works no matter what type of shape we're looking at. So let's start Q at A is equal to, let's look at the pieces we're going to break this into. So I will break off there because there's a change in geometry. So we'll start by looking at the area of our top flange, and then the other area we'll use will be this little chunk between the neutral axis and the top flange. So we'll call this area up here A1, and this area is A2. So centroid of this one is going to be located 1 centimeter down from the top surface of the beam. Centroid of this, so here for the first time we've got kind of our neutral axis has moved to a integer value. So our total height here is 10, and then we came down 2, so this distance right here is 8, and then this is 6.5 centimeters. So this distance right here, this is 1.5 centimeters from the neutral axis to the bottom of the top flange. So that means that the centroid of this little piece right here is going to be 0.75 centimeters up from the neutral axis. Okay, so let's go ahead and plug in using variables first. So A area prime for A1 plus y bar prime for A1, I'm sorry, not plus, times y bar prime of area 1 plus area of A2 times y bar prime of A2. So Q for A using the geometry above A. So let's, area of area 1 is 2 times 8, so 2 centimeters times 8 centimeters. I'm just writing these out so we can kind of get used to the practice of why our units come out being centimeters cubed. And in reality, when I go to plug this into the shear equation, I'm going to convert my centimeters cubed back to meters cubed probably, right? So that all my units work out. But I'm just doing it in integer centimeters rather than like 0.08 meters. Okay, so 2 times 8 gives me the area of A1, and then I need the distance from the centroid of A'1 down to the neutral axis. So in this case, we have 1 centimeter to get down to the bottom flange, and then we have another 1.5 centimeters to get down to the neutral axis. So it's times 2.5 centimeters. That gets me all of this part here. And now let's look at the contribution of area A2. Area A2 we said is 1.5 centimeters high by 2 wide, so 1.5 centimeters times 2 centimeters. That gets me area A2. And then the centroidal distance we talked about a minute ago is half of 1.5, so that's times 0.75 centimeters. Let's plug all that in. 2 times 8 times 2.5 plus 1.5 times 2 times 0.75. I get that's 42.25 centimeters cubed. Okay, let's do it using the area below and see, we should come up with the same value. So now there's just one area below, but the last time we did this we had an I-beam. I had to keep track of a flange below. So in reality, it would have been quicker for me to find Q by looking at the geometry below point A instead of above, but we wanted to do it both ways here. So I'm not even going to shade in that area. Let's just write out the equation for using the bottom, the geometry below. So say Q below A is equal to, we'll call that A3. I'm not going to write it out there, but the area of A3 would be its height here is 6.5 centimeters times its width, 2 centimeters, times the distance from the centroid of that. So centroid is going to be 6.5 divided by 2. So that is 3.25. Okay, so 6.5 times, oops, 6.5 times 2 times 3.25, and we get equals 42.25 centimeters cubed. So they match, but definitely quicker to do it using the geometry below because it's not a composite shape, right? Just one simple rectangle. Okay, let's move on to our next one. I asked you, oh, we didn't talk about t. T at A is equal to whatever this distance right here is. So that's t is equal to 2 centimeters. Okay, let's look at B. That's this color here. So if we are now looking at a section through B, again, I could do above or below, but hopefully you're seeing it's going to be a lot easier if I do it based on the section below. So Q at B is equal to A prime B times Y bar prime B. So QB, area of B, I'm given that it's 2 centimeters down from the neutral axis. So the neutral axis is at 6.5, so it's going to be 4.5 centimeters high times the width of 2 centimeters. And now the distance from the centroid axis to neutral. If we're at 4.5 here, so 4.5 divided by 2, that gets me to, so this distance right here, the centroid, that's 2.25. So the distance is 6.5 minus that. So 6.5 minus answer, so 4.25 centimeters. So that times 2 times 4.5, and we get QB is equal to 38.25 centimeters cubed, and at that point T is still 2 centimeters. Okay, and you can see that this value is less than the value at the neutral axis, which is what we would expect, right? Shear is always at its maximum there at the neutral axis. Okay, I put one more in here. I feel like we've kind of got the point by now, but let's do it since I marked it out here at C. So pretty easy one, right? There's just a single rectangle, so Q at C is equal to area at C, prime, times Y bar at C prime. So that area of C is 2 centimeters by 1 centimeter, so 2 cm times 1 cm. Centroidal distance is going to be half, the centroid of it is 0.5 centimeter away from the bottom, and the neutral axis is 6.5 centimeters away from the bottom. So the distance from here to here is 6 centimeters, so 6 centimeters. So 2 times 1 times 6. So we get here it's down to 12 centimeters cubed. And again, that makes sense. This should be a much smaller number because there's a much smaller piece of the beam that's being held on by the shear stresses that are spread across the plane at C. Okay, that's finding our Q for 3 different locations along a T section.